Hi everyone. So we are discussing count subarrays with majority element question today, and we are going to solve this using Fenwick tree. So let's get started. So let's forget about the question for now. I am going to first talk about Fenwick tree, and then we'll proceed to the question. So to explain what's Fenwick tree, I'll use an example. So let's say I have 8 boxes and every box has some number of candies. So, of the particular fruit flavor that I've denoted here, for example, apple candies, grape candies, something like that. So, every box has those many number of candies that are mentioned here in the array. And now let's say someone asks us that, how many total number of candies are there from box 1 till box 8. So what we'll do, we'll go to every box, we'll calculate the number of candies and then sum it up all, right? This is fine. Okay, what happens if that person comes again and asks us, okay, fine, now tell me how many candies are there from box 1 to box 5. We again will, open up every box, count the number of candies, sum it all up until box 1, from box 1 till box 5, and then tell the answer. Okay, twice is also fine. But that person keeps on coming back and asks us, every time a different number or something, how many total candies are there from box X up until box Y. So, going back, counting every box candy, coming back, summing it all up, and doing this in a repetitive manner is very, irritating, to be honest. And I don't want to do that. So, so we come up with a smart idea. So let's talk about what the smart idea is. Let's say we have some helpers, and those helpers basically, already have, some in between ranges, some ranges. So, for example, let's say this helper has sum of first 2 elements. This has first sum of fifth and sixth element. These have, sum of 5, 6, 7, 8 elements, something like this. So there are helpers. So instead of summing it all up, going back, looking manually, we can just see. We can just ask the helper and they will basically tell us, right? So we don't need to go back and do the same task in a repetitive manner. So now let's say that the question is, how many candies are there up until box 6? Now we don't have to do this manually because we have helpers here. See, we have 1, 2, 3, 4 and then we have 5, 6. So if we ask these two helpers here and whatever the answer we get, we sum it up, we are going to get the answer, right? So now we did not go manually and check all the boxes from 1 to 6. So that saved a lot of time. So the helper that we were talking about is actually called a Fenwick tree. So the idea behind the Fenwick tree is that it basically has this thing called index and minus of index to get the last set bit value, and that will be the number of boxes that is it's going to hold the sum for. Okay, let's not try to understand this right now. I'll explain this later. But see, this one thing here. We have this for, this element 1 at index. We have 1. For 2, second index of the tree holds 2 values. which two values? So it will always end in the current value. So ending 2, and if we had a length of 2, it would obviously hold 1 and 2, right? So notice that every cell holds that sum for that particular index along with some other elements. So 3 has a length of 1, so it's only going to hold the sum of only one element, which is current, that element itself. So you see the current ending summation index is the same as that of I in the tree, right? So the length of the elements it's going to hold is calculated by last set index, which is calculated by index and minus index. So we'll come to this. But let's first understand the binary computation. So let's say we have a number called 6. So this is a decimal number, right? So let's convert this to binary. So in binary, 6 goes like 10110. So for understanding purposes, right now, we are taking just 3 digit right now. So now what happens is 10110 is how 6 is represented in binary. Now what's the last set bit of 110? So it's this. So if we say like if we from here up until the end, what's the value? 10. And how is 10 represented in decimal? 2. So 6, whatever, like ith element, if I is 6, it's going to hold sum of 2 elements. Now which 2 elements? We know that end element will always be this ith element 6, and one more element it will hold before that. So 5 and 6. So now 6th helper or index 6 in the tree is going to hold the sum of 5th and 6th index element from the array. So this is the entire binary computation I was talking about. So now let's talk about the logic of index and minus index. So this is basically done to get the last set bit. So yeah, so we want to get the last set bit. So let's say our, let's say current index is 2. So what would be 2 and minus 2? So in, it's stored, minus 2 is stored as 2 complement. So what we are going to do is, let's first convert 2 in binary. So we are taking 4 digits currently. Now 2's complement will be, let's start with 2. We have started with 2, 0, 0, 1, 0. Now we are going to flip all the bits. So 0 becomes 1, 1 becomes 0, and 0 becomes 1. Same here. Now what we are going to do is add 1 to the flip bits. So this plus 1. So now we get 1110. So this is our minus 2 representation. Fine. Now we are going to do AND of 2 and minus 2. So the only set bit would be the last set bit in both of the elements. So when we do AND, we are going to get last set bit. And this value in decimal is 2. So the answer for 2 and minus 2 is 2. It means our second helper will store sum of 2 elements. Which 2 elements? Firstly, so it will end with 2, that is definitely. So it will store sum of first and second elements. Okay. I will come to a little bit more explanation, but let's first see this, what we are trying to talk here. So remember from the previous slide as well, we were saying that the helper, which is the Fenwick tree here, is always going to remember boxes ending at itself, right? So for helper 8, we see the ending index is 8. For helper 7, the ending index is 7. For 6, the ending index is 6. For 5, the ending index is 5. For 4, the ending index is 4. 3, it is 3. 2, the ending index is 2. And for 1, it's 1. So this is one observation I wanted you to make. Now let's go backwards. Why will we go backwards? I'll come to that, but let's see how do we go backwards. So the formula for going backward is, if we want to get some value. So let's say I have this index. So how will my index decrease? It's going to be minus equal to index and minus of index. So this is the formula. We'll see why. So let's see. Let's say we are trying to build a Fenwick tree. Firstly, we'll start with this. Always remember that Fenwick tree is one based indexing. So initially our tree is assigned 0 0 0 0. Tree is empty right now initially. And this is our array, for example, 1 2 3 4. We have 4 boxes and these are the values. So we'll start with 1. What are we going to do is we are going to update 1 with the value of 1. Update 1 means index 1 with the value of 1, which is stored here. Okay, so now we start at 1. You remember the formula? The formula for update or insert is index plus equal to index and minus of index. So we start at 1. Then what we do is, we are going to store whatever is the value. What's the value here? 1. So we are going to store whatever is the value present here plus 1. So it was 0 initially. We did plus 1. So it became 1. Now we are going to iterate up until my I is, I goes out of bound. So now my formula says update index to index and minus index. So 1 and minus 1 is 1 and 1 plus 1 is 2. So now I come here and what I do is whatever value was here, I add 1 to it. So 0 was here initially and we added 1. So it became 1 here. So now again we are going to update index. So now 2 and 2 plus 2 and minus 2 is 4. So now we go to the 4th index and we add 1. So this is, it was 0 here, now we have added 1. So right now the value is 1. Again, now my 4 plus 4 and minus 4 is 8. And this is out of bounds. So we are going to stop here. So after I called, update 1 1, this is how my tree looks like, Fenwick tree. So now, let's say we want to update index 2. Okay, so what's the value? It's 2 here. So this is the value that we are going to update. So we are going to start with add 2. And what's the value? Whatever is there, we are going to add 2 to it. So 1 was there previously and we added 2 to it. So now the value becomes 3. Now we are going to update index using this formula and we go to index 4. And we are going to again add 2 here. So now it was 1 earlier. So it became 3. Now when we update the index again, it goes 8, which is out of bounds. So we stop here. Okay, moving on. Now we say update 3, 3, which is update index 3 with the value 3, since 3 is present here. So now our current value is 3. Now we start at 3 and we add 3. So 0 was present here initially. And from 0 we went to 3. See the change? It's plus 3. And then when we do 3 and minus 3, it comes to be 1. And we add it to 3, it becomes 4. So now at 4th index as well, we add 3. Which becomes 6 right now when we do 3 plus 3. Okay, now at when we do in update index again, when we update index using this formula again, what happens is it goes out of bound and we stop here. Now we do the same thing for 4 and the steps are mentioned here. So we add value of 4 here, which is like 6 plus 4. And this is what we have done. From 6 we went to 10. And when we update index, it points to 8, which is out of bounds. And we stop. So this is how the tree looks like after we have done 4 insert or update calls. Okay. Now, let's say now that we have this tree and someone asks us, like, what is the sum from index 1 till index 3? Now, I don't need to go to array and, do all of those operations. What I need to do is, I just need to follow this formula until index is greater than 0. Since index is starting 1 here, right? So now we start at 3. Since we want up index sum up till index 3, right? So whatever is the value here, we're going to add it to sum. So that's why our sum is 3 right now. And then we decrement our index using this formula. So now we go to second helper. Okay. Now when we go to second helper, what happens is the value here is 3. So that's why we add it to sum. Okay, now we add it to sum. And then when we, apply this formula, what happens is our index is 0. Now 0 is invalid index. So that's why we stop here. And our sum is 6. What's the sum from index 1 to index 3? 6. Now let's verify actually what we are talking about. So this actually here, this stores sum of only one element, which is index 1. Now this stores sum of two elements, which is 1, 2. Now third index stores sum of just one element, which is 3. Now remember we wanted a sum from index 1 till index 3. And to look for that, we need these three sums, right? And we want tree of 2 plus 3, tree of 3. And that's the entire thing that we did here using this formula, and we got 6. So it's working fine. Now let's see how does it work fine actually. Let's understand this more better. So the intuition is that firstly, what Fenwick trees does is that it breaks every prefix into blocks of sizes. We'll come to this in upcoming slides. So each helper block is of the size of power of 2. And it ends at its own index, as we saw. Now it's designed in such a way that when we query, there is the blocks don't overlap when we answer. So it's designed in such a way, and we are going to come to this. What does it mean? And note that when I'm saying when I query, it's designed in such a way that the blocks don't overlap. Remember the word query. And the time that it requires for query and update is big O of log n. It is usually if you go to every element and check, it is big O of n. Now from big O of n, we have reduced the time complexity to big O of log n, which is great savings. Okay, now firstly we'll just decode why power of 2. So let's understand. Let's say I wanted, sum from in box 1 up until box 13. How could we actually split this if I had to do it? So I could have 1 and 2, then I could have 3, 4, 5, then there's a wall, then 6, 7, 8 together, then there's again a wall, then 9, 10, then there's again a wall, and then followed by 11, 12, 13 index. There's also another way, this. There's another way, and there are 1,000 more ways to split. If I had a free will to split numbers from 1 till 13, I have a lot of ways. And this is literally confusing when I'm trying to code something and there's a lot of ways to solve, split this. So which way to go is very confusing. So that's why we have power of 2, because every integer has a unique power of 2 decomposition, and we'll see how. So this is the rule that every block size must be something to the power, power to the 2 something. So which means the allowed block sizes are 1, 2, 4, 18, 16 and so on, right? 2 to the power 0, 2 to the power 2, 2 to the power 1, 2 to the power 2 and something. So these are the allowed valid boxes. And every number has a unique power of 2 decomposition. Decomposition is the keyword here. And there's only one way. So, and this is, remember this index and minus of index. So it gives this last set bit. And this last set bit basically gives us the size of the block. And it instantly tells us which block to go. So let's say I had 13. So firstly, what's the biggest block that could fit 13? It's 8, right? Because 16 is like a very big box. So it's 8. Then after 8, how many numbers are remaining? 5. Now what's the biggest block that can store 5? It's 4 after 8. So then what is remaining? 1. So then 1. So if we go to index 8, 4 and 1, we are going to get, sum from 1 till 13. So that is as easy as is. So that's why we have chosen power of 2. Now, the question was that, like for every element, we have this balance, and we'll come to what balance is. Now, this is the algorithm. So, we are saying, actually the question, let's first come to the question. The question says that we have an array and we have some target, let's say T. So, in this array, we have to check for how many sub-arrays. Now, my count of T is greater than half of the length of array, sub-array. So, L by 2. Obviously, L is for sub-array length. So, whatever sub-arrays this equation holds true, we have to return the total number of those sub-arrays. So, this is the entire question. Now, my algorithm is just like this. Now, what happens is, we have a balance, which is a running prefix sum. And I'll come to what running prefix sum is in more detail in later slides. So, this is our running prefix sum. And what we do is, in answer, which is our count variable, if, x minus y is positive, the current score is positive, we'll come to what this means later. So just mean that when score is greater than 0, we add it to answer, and then remember current balance as well. So that is how we update tree works. And we'll come to how Fenwick tree is actually integrated here. And so basically here the complexity would have been big O of n to have like lookup or query or get index, but it is reduced to big O of log n because of Fenwick trees. Now we'll see how that happens. So firstly, let's walk through the Fenwick tree code. So this is a class Fenwick which we have designed, which has like an array tree. Now remember, Fenwick tree is always 1 indexed. So our indexing starts from 1. So let's say I have n number of elements. So if my indexing starts from 1, but in Java it starts from 0. So that's why we have initialized the tree to size n plus 1. So this is the reason. Now we have two methods here. First one is update and the second one is query. Now remember what happened in update. We wanted to add a value to a particular index, and then we wanted to update index with index and minus of index. So that is what we are doing here. And to that particular index, we are adding that value. So that is what we did here. And up until index is not out of bounds. So that is what we are doing here. So this is as easy as is. Now we come to the query part. Now the query part says that what do we mean by query? So we wanted to get the sum from x range to y range, right? So what we did was we went to a particular index and then we went back to a previous index using index and minus of index, and we minused it from the index value. And then we added it to sum, current sum, that particular tree of index value, and then we return sum. So this is as easy as is. Now moving on, we have second part of the question, which says that we have to count subarrays where target is majority. Okay. Now in this array, let's say this is an array. So if we had to do this manually, our target is 2. So what's the count of 2? We would actually count it, right? So then count of 2 is 2. And we do not really care what the other element is. We just need to know that if an element is 2 or not 2. So count of other element is 1. So now my count of target is majority, right? How is this majority? What's the length of the array? 3. Now 3 by 2 is actually 1 in integer, and my count of target is 2. Now my 2 should be greater than 3 by 2, which is 2 should be greater than 1, and it is correct. So that's why this is a valid subarray. Okay. Now what if we don't really want to count manually, the number of 2 and the length of the subarray for every particular subarray? Then let's say we come up with some trick. Now what we do is, we are only bothered if a number is equal to target or not, right? So let's say whenever we encounter a target, we do +1. We actually write +1 in our tree something. And then whenever we don't encounter a target, what we do is we write -1 to the array. Like let's say from this array, I would, if my target is let's say 2, then what happens? I write +1, and then I write for 1 I write -1, for 2 I write +1, and for 3 I write -1. So it means that whenever we encounter a +1, it means we have found a target, and whenever we encounter a -1, it means a target was not there. We actually do not need to know what number is there. We just need to know if a number is target or not target. So can we do this? We can obviously do this. Okay. Now since we can do that, this is the array that we'll get. +1, -1, +1 and -1 if target is 2. That we saw. So we are going to calculate the score of subarray now. What it means is, we got this array. Now what happens is, let's say the count of target is x and the count of others is y. So our score will be 1 into x, since x will be assigned +1, and -1 into y for other elements. So what will be the sum for it? It will basically be x minus y, right? If we solve this, we are going to get x minus y. Now, our question says that if this is positive, it means our target is majority. In a valid subarray, the score will be positive, right? Or it will neutralize. So if score is 0, it means the number of +1s is a majority, right? Okay. So now this is the code for counting majority subarrays. Now this is the length of the array n. Now this is the Fenwick tree that we are calculating, that we are creating. So why 2 into n plus 1 is the size of the array? Let's say I have array of size n. So let's say worst case, all of my elements are non-targets. So and the total number of elements is n, and all of them are non-targets. So -1 will be assigned, so it will be -n. So this is the minimum value, right? -n is the minimum value. What's the maximum value if we do +1 -1? So all of the numbers would be targets. So n would be the maximum number, right? Or mid case 0, right? No targets. So obviously anything in between -n till n. So how many numbers are there in between -n up until n? So it is 2 into n plus 1, right? So that is what we have done here. Okay, now what we are doing is, we are now seeing we are updating. Now we have this balance. What does balance do? It's basically a running prefix sum. And instead it should have been 0 initially, right? But why have we done it -n plus 1? Okay, you remember that our Fenwick tree actually started with one index. So 0 would be actually, we need to shift 0 to n plus 1. So that is why we want to make it positive and one index. So that is why we have shifted everything by n plus 1. So 0 is n plus 1 here. So that is why n plus 1. Now we have seen, there is this thing called, we have seen balance once, which means 0, let's forget n plus 1, we have seen 0, sum, subarray once. So this is a wall kind of, and we have seen it once, whose sum is 0. And we are going to update that in the tree. Now, we have this answer variable and we are going to return it in the end. Now what we do is we traverse through every element of the array and we check if it is equal to target. If it is equal to target, we do a balance plus plus. Balance is basically a running sum. You know how we calculated score x minus y. X is the target and x is the number of target and y is the number of non-target. So we are calculating the score here. So whenever we encounter a number is equal to target, we update balance. Now our balance is, let's say, 0 and we update it to 1. However, it is one index, so it can't be 0 anyways. That's why we've shifted it to n plus 1. So now we'll again shift 1 to n plus 2. So that is how we are going to do the shifting. But for understanding purpose, let's say this is 1. So now balance is 1. So it is positive, right? Greater than 0. So what are we going to do is, we are going to check if, there are how many subarrays with balance minus 1. So 1 is my balance currently and we are going to check how many subarrays are there with balance 0. Now with balance 0, I have one subarray in the tree, right? So now we are going to add it to 1 answer. So now my answer is 1 currently. And then we are going to update the tree with balance as we have seen balance once. Like one more time. Now what's the balance? It's 1. So now we have seen 1, or rather shifted by n plus 1 places. So we've seen another wall which is 1 once. Okay. Now this is going to continue up until every element of the array. Now I want to understand if this is valid. Let's say I had length 1 array with 2 here and my 2 was target. Now let's say my balance was 0 and we never said to our tree that store balance 0, that we have seen balance 0 once, stored this somewhere. What would happen is our balance minus 1 would have returned 0. But if you see the, for 2, element 2, we do have a possible subarray. What's a subarray? 2. So 0 was the incorrect answer. That's why starting the first index up until any, number of elements for that particular subarray, we require the first wall. And that's why we are having this line, which is line 36 for the first wall. So starting 0th element of the array, if there's any valid subarray, this will help us count that valid subarray. Okay, and then we return the answer. So the time complexity is big O of n log n. Why big O of n? We are iterating through every element of the array and then we are querying, which takes big O of log n time. So that's why big O of n log n. And space is big O of n because we have a tree.